I actually haven't seen that much activity all day today.
Oh, really? Oh, really? That's
Yeah, like just,
surprising.
I was thinking about, I had, how many students I had at office hours last night, Sunday?
How many? 0.
0.
Really?
Exactly. 0. Not even anyone remote. Now, SC did walk in, but she didn't ask me any questions. So, it doesn't count.
I just work, and in case I have questions, you're right there.
Exactly, yeah. So I think I was wondering to myself, I was actually writing my nightly diary entry. I keep a diary. Aw, isn't that cute? No, it's like a daily reflection, and it's really useful. If you can find the time to do one yourself, I think you would enjoy it. But I was speculating, how can this be? This is a hard assignment due tomorrow, and no one's asking. And I think one thing that does happen is that the students kind of get spread out quite a bit. So we have, some students trying to finish up homework 8, but we actually have a significant number of students that are finishing up homework 7. And that's not a bad thing, I think. That's a pretty good job if you're finishing up homework 7. You're not that far behind. You're going to do a good job. You're going to get a good grade. And then we got students who are on homework 6, right? They're still in it. And, so everyone's just kind of spread out. And people just don't, they're not feeling the intensity of that deadline like they might have when they were doing homework 4 and 5. So I think that's a big part of it. Anyone else speculate? Anyone else have any ideas why there's no questions anymore? This happens in all my courses. Students just stop asking questions. And I think in 494 and 440, it's because the students have moved on to their own projects. So, there isn't anything specific they want help with. What do you think?
I speculate maybe some students are burned out. Maybe some students just wanted to queue 30 games of League of Legends.
I didn't want to say that one, but I was thinking that, definitely. There's a certain element of, oh, shoot, have the students given up? I don't think they've given up, but I think at a certain point, you kind of accept, okay, my 100% is gone. I'm not going to finish every test case. And that kind of relieves some pressure to go to every office hour session, right? And that's just how it goes. Hopefully you don't give up completely, okay? If you give up completely, you might actually fail the course. If you take it easy on yourself and let yourself give up on some test cases, you're going to be fine, okay? And hopefully your mental health will be better. And you might even find yourself having a better educational outcome because you're not sweating the small stuff, right? You can kind of focus on the bigger picture, and you can do the assignments and get through the important parts of each assignment, hopefully. Okay, how did homework 8 go? Congratulations to all of you for finishing it. Well, most of you, some of you. How'd it go?
Pretty good.
Yeah. Got a lot of feedback, though, saying you preferred this to homework 7, that it was easier than homework 7. And I've got really good news for all of y'all who think that. Homework 9 is just more homework 8. Okay? In fact, you can use the same technique in homework 8, right, in which you created a C++ built-in component. You're going to do the same exact thing on homework 9. And the hard part of homework 9, and in reality this isn't all that hard, is just kind of adjusting your thinking and realizing the value of C++. C++, we're going to talk a lot about memory management today and memory layout. C++, part of what makes it so important and why people put up with C and C++ and all the shenanigans it brings to the table, the complexities it brings in, is that C and C++ give you that elusive control over where things are laid out in memory, how big your data structures actually are, and that can be everything when it comes to performance. I'm going to show you some really crazy experiments in just a few moments. I got Visual Studio open. I'm going to show you some experiments that will just blow your mind in just how important it can actually be to make sure you're thinking about where you're putting things in memory, where are your objects in relation to each other, how are you loading them in, and how big are those things? And in Lua, In JavaScript, in Python, you just don't, in these dynamically, these high level, very friendly, dynamically typed language, interpreted languages, you just don't tend to have very much control over how big your data types actually are and where they're going. And that can mean that C++ is the only tool for the job. When you need that performance, it's the only tool, okay? Or maybe you go for something like Rust or something else. But that's why people put up with C++ and why it is still so beloved, okay? All right, everyone, let's really get started. We are lecture 19. Has it gone by fast? It has for me, but I'm not the one programming the assignments. I'll tell you, when I was launching this course, and I was the person grinding the assignments because I had to make them, and grinding the lectures because I had to make those, that first semester was hellish. That thing never ended, okay? But hopefully it's going by relatively quickly for you because it is really not that far out now. We are just 2 very short weeks out from that exam. And actually, this is the final week of your programming homework assignments, your auto-graded homeworks. I know. Don't be too sad that it's ending. Be glad that it happened, okay? And for those of you who are a bit behind, well, at maximum, you've got 2 weeks of those difficult auto-graded programming homework-related stuff because the auto-grader off date is 2 weeks from today, which means you can keep programming and submitting to the auto-graders after April 4th at 4:30 p.m., but you're not going to get any points for that at all. It'll just say, thank you for playing. Here's your score. By the way, this isn't your actual score. I'm not putting this into Canvas. Basically, the auto-graders still give you a score and grade you. They're just like, nah, I'm not putting that into Canvas. And typically, after the auto-grader off date, if one of the auto-graders dies, I just kind of press F in the chat, Like I'm not driving in to reset that thing. Maybe if people ask nicely, I'll go turn it back on again, but probably not. We just kind of leave it going and see how long it can last. So last year, most of the auto-graders made about a month. I think one of them died early for some reason, but they made it a month. And usually what kills it is Windows forces an update. I can't figure out how to turn that stuff off. And I haven't set up the bot to automatically load in and launch the program yet. So every time that happens, I have to drive in and manually relaunch that thing. Ooh, painful. The MMO architecture course is really nice because the only server we're going to care about is Ubuntu servers. And even I might change it to a different Linux distribution, but it's going to be Linux all the way. It's also going to be remote Linux autograders. That means you can be messaging me. I'm in bed at 4 a.m. Austin, turn the autograders back on. What happened? And I can be in my bed with my phone and I can relaunch them if I need to. So, hopefully that won't be too bad. I'm currently, keep this somewhat down low. I'm currently trying to figure out how I can do a PhD in Europe. People think I don't have my PhD. People think I'm a doctor. I'm not, actually. I'm one of our few faculty who have a master's degree. I'm trying to figure out how I can teach game engine architecture if I'm in Europe every other month for a month straight. I'm going to have to take my autograders with me? Maybe. I don't know. Don't know how the TSA is going to feel about that. But we'll have to see. Anyway, so being able to do remote autograders and focus on Ubuntu only is really, really nice because every darn operating system has interesting, unique quirks and ways to mess us up good, like the crazy updates. Mac loves to blue screen of death more than Windows does. Linux has its own quirks, especially when things get overloaded and Linux decides to just start killing processes willy-nilly, right? Still trying to figure that one out. Anyway, all right, let's get off that tangent and on to the important stuff for you. I want to introduce Adventure Game Studio. This is a really cool one, okay? This is a fairly old game engine, 1997, created by Chris Jones. It's famous in my mind for one series in particular, the 5 Days a Stranger saga. If you've never heard about that, well, one of the reasons you might hear about it is that it was created by a pretty famous developer. His name is Ben Yahtzee Crawshaw. If you've ever heard of zero punctuation, that's the guy, okay? And this is a very fun, very fun adventure game series. It is a horror game series. It has puzzles, it has great characters, and it usually has dynamic interactive gameplay. At some point, the killer at the heart of the story's mystery is going to be chasing you down and trying to kill you. And you can get great morbid endings out of that if you get caught or make the wrong decision. And so I encourage you to give these a shot. They really do have the feel of those old point-and-click LucasArts style games. You can see some footage of the editor. Here is a kind of a YouTube tutorial from, who made this? Julie Minamata. Okay? She kind of walks you through how you can make games in these engines. Now, I'm a terrible 2D artist, so I'm just kind of missing a big part of my brain that would really make an engine like this sing for me. I do like writing dialogue. I do love creating puzzles, but if everything just looks like rectangles, then that's just not going to be good enough. But you can kind of see this game engine allows you to write dialogue, create characters, create icons. I think it has a scripting language. It has a global variable system. In many ways, it reminds me of RPG Maker. Yeah, so function, look at this. This, to me, looks like JavaScript. A fantastic choice, okay? Lots of web devs out there who already know and are comfy with JavaScript. You can go through and you can actually paint. If you look at this really carefully, she's actually painted the walkable areas of the 2D art down here. So you can provide some art, and then you have to define and help the engine understand where can I walk in this area. Super, super cool. So anyway, this engine was used to make a number of really fun games. I think these games are free. Warning, there appears to be a Trojan lurking within one of the default templates of Adventure Game Studio. Well, that's a bit of a bummer, isn't it? You'd think they'd do something about that. And I think I found this via people complaining on Reddit about this. So, yeah, be a bit careful, okay? Always be careful about what you download. And in case you accidentally get ransomwared, make sure you're storing your most important stuff in the cloud probably, so that even if you do get ransomware or something horrible happens, you can just clone your most important work and files to the new computer you end up working on. Or you can just wipe the entire computer, pretty much guarantee it's going to be in a healthy state again, and there you go. Adventure Game Studio. So you got this cool website. It's totally free, I think. I think it's open source. Yeah, just awesome. You can draw walkable areas, you can create characters, inventory items. The scripting language, I'm seeing here, apparently it's based on C, but it's kind of its own thing. I guess I don't know a whole lot about this. I haven't learned a whole lot. It looked more like JavaScript to me. So that's what I would say it probably is. Anyone have any questions or comments? If you're bored, play some of these games. And, the way to play these old-style games, in my opinion, is try and play them without a guide, but find a guide and have it ready to go. And when you get confused or lost, start that 10-minute timer. And when 10 minutes is up, you go and grab just the next part you need, and then you're back into the game. It's a really nice way to enjoy those old-school classic games with their difficulty, but you're kind of evening the playing field, because you know how you were supposed to play those old games? Those old games can't be experienced the way they were intended to be experienced. Why? Because in the 90s and 80s, the way you were meant to play those games, can you tell me the way you were meant to get through them with those super difficult puzzles? Yes?
Go, talk to other friends that play the game.
Exactly. The games were designed with the intent and expectation that other people at your school or in your neighborhood or in your friend group were playing the same game or had already played it. The point was to get you talking to your friends at the lunch table, the cafeteria table, and talking about, oh, you didn't know, dude, you missed that super important item. Yeah, you have to click this one little pixel in the wall. I found it totally by mistake. Oh, really? Yeah, really. Oh, that's awesome. Okay, yeah, can you come over and like help me find it? Yeah, okay, I'll see you this afternoon, right? And that was how you're supposed to do it. And so it was a very social thing. Now, almost no one does that these days. And everything seems to be kind of crowdsourced via wikis, which I think take away some of the fun. The wikis are a bit too powerful, and you're really meant to be scouring this game together. I remember very, very clearly when I was a kid playing through this brand new revolutionary game. It was called Pokemon Red. That was the first Pokemon, if you didn't know, the first Pokemon game. And I was watching the Pokemon anime with my friends, and it was awesome. I always knew who that Pokemon was. And I discovered the way to get the big, chunky Snorlax out of the path. That, like, after Mount Moon. I don't remember the Lavender Town, was it? The Spooky Town. There's, like, a Snorlax nearby. And it was like, oh my gosh, my friend group and I didn't know how to deal with the Snorlax. There's this big, chunky Pokemon sitting on the road. We can't get through. And I discovered you had to go do this crazy dungeon and get this flute. And then, okay, what's that for? You have to go play the flute near the Snorlax. I think that wakes it up. You fight the Snorlax. Hopefully you get it into a Pokeball, and then you can go by. And I remember, oh my gosh, as soon as I figured it out, I was on the phone talking to my friend and telling them, like, oh my gosh, this is what you got to do. And they were like, I can't believe it. Good job, dude. And that's just how it went. That's how you beat games. People would kind of stumble upon what to do, and you would have a really good time sharing this with your friends, and it was like a community local experience. These days, you can beat any game you want just by hitting up YouTube, and it's not the same feeling. It's simply not. Okay? So anyway, that's why a lot of those puzzles were designed to be very hard, and why that's a little bit of a fool's errand these days. You can't defeat the wiki. You can't design a puzzle that's going to defeat the wiki unless it's an obscure game, at which point there is no wiki, there is no YouTube walkthrough, and that's part of why I love itch.io. You can find pretty awesome games no one has played, but you're going to play it. Okay? And you can get a little bit of that magic back. Sometimes, if you can't figure out how to proceed, you can literally ping the developer with some footage, and maybe they'll give you a hint. And they love to talk to you because you're like the one person playing their game, right? It gets you a little bit of that back. I don't know. Don't feel bad that you missed out on some of those experiences as Zoomers, because they're experiences you enjoyed that I didn't get. All right. Every generation has a unique flavor that they experience in their childhood. And I think it's really fun when the generations talk, because sometimes they don't. They talk and they can kind of share that magic and learn more about what it was like, I don't know what it was like to grow up with your first game being Super Mario Galaxy. That's like luxurious, okay? That's crazy. I grew up with Crash Bandicoot. Things were a little bit more blocky, but we kind of liked it that way, all right? It's kind of nice. That's why all my stuff, if it's 3D, it's probably low poly. That's why if you take 298, you're making the low poly characters. Stephanie O'Malley, the assistant director of the Dudestat Center, I'm driving her crazy because she says, Austin, we should teach them Maya, and we should go ZBrush, get them into those cool, realistic, high poly characters. And I'm like, no way. No way. We're making Crash Bandicoot characters with 100 polygons tops. It's going to be awesome. All right? Anyway. Okay, that's the end of that tangent. That's like the second tangent I've had already. We're running out of time. Okay, so, so your final auto-graded assignment, homework 9, has launched, and I think it's appropriate that we kind of had this spike in difficulty at homework 6 and 7, and now we're kind of just going down the hill, and hopefully that's nice for you. It's not going to be a big stressful thing. Homework 9 is pretty easy. It's a pretty easy homework, but I think it's kind of a fun homework. The results are beautiful, and I think it's very interesting and fun to think about performance, and it's not very hard to do so. Data-oriented design is not this crazy hard thing unless you want to make your system very flexible, ECS is not something we require in any homeworks in this course, but making the best ECS, which we'll talk about what that is in a sec, making the best ECS that's super flexible for your engine, that's actually kind of hard. But that's something you can do for your custom features, maybe, or after the course ends. Okay, so expect the assignment to be a little bit shorter and a bit easier, and I think you've earned it. I don't actually see this as a design flaw anymore. Last semester, I was rushing to make the homework 9, and so it was a bit shorter for that reason. Now it seems that maybe we'll leave it a bit shorter because the students really appreciate that. Maybe, we'll see. In particular, if you have any particular experience or feedback that you want to share on homework 9, then homework 9 is really what I'm listening for very intently because it's not, still new, very new. Okay, so what about this homework 9 anyway? What about it? Well, homework 9 is just a tremendous opportunity to explore what data-oriented design means. Actually, if you look at the new name of this course, it's no longer EECS 498 Game Engine Architecture. Does anyone know what the new name of the course is? I've said it a few times, but maybe not the full name. Yes?
No 404. I don't know what that is.
It is EECS 404 Game Engine Architecture and Data-Oriented Programming. And that's, I feel like we want to work data-oriented programming into some of the earlier homeworks maybe, because if it's getting half the name of the course, then maybe it should get more than one assignment. But, that's something we'll figure out later. Homework 9 is literally called data-oriented design, and I often use data-oriented programming and data-oriented design just they're synonyms, right? They're the same thing. And this is one of those features that you really want to be in C++ land to be able to manipulate and design the way that you access data to get it performing really, really well. Because when people want to use particles in their game, they don't want to use 5 particles. They don't want to use 500 particles. They want to use 50,000 particles, okay, or more. And the reason they want to do this is that particle effects can give us some of the most dynamic, interesting, and sometimes realistic, visceral effects that humans experience. So we have had some snowstorms. In fact, today we had snow coming down, and I'm sitting in the Pierpont shop. What is that called again? It used to be called Hugo's. Blue Market? Maybe. And I'm buying my Celsius, my second energy drink for the day, and I am just looking outside at the snow and just, man, that is beautiful, right? A good blizzard is like the only time you'll ever see that many particles without any slowdown or lag. And so you really got to enjoy it when you can. But also, you can see up here, things like fireworks are usually done via a game engine's particle system. And over here, you can see we have some sort of like firefly or fairy with this cool, like, reddish glow that is maybe coming off of her. Maybe she's flying up to us to give us a hint or something, like in Legend of Zelda. Hey, listen, right? Who knows? Who knows? But it is very interesting. It's eye-grabbing. And we are moving from this game engine that used to be static, but now it is rich with this physical interaction, right? Physics, realistic physics. And we're moving to this world where we can have realistic physics, we can have also beautiful particles to mix in with that. So you can imagine a very snowy game, a platformer where you're trying to roll and push snowballs around, but we also now can support falling snow. We can also support little bursts of snow as you step through the snow, right? And so our engine just keeps getting more and more things. This is how modern, featureful, industry-standard engines develop. You are just adding more and more features, and you're thinking about what should I add next, right? If we keep going, we might add an editor, like we saw from Gavin last week, and suddenly you're asking yourself, is this not literally just a 2D version of Unity? with a few missing features. And how valuable is Unity again? Do you remember? We looked it up, didn't we? What's the Unity? Ooh-wee, okay, a cool 8 billion, all right? Imagine if someone in this course, a team, IPO'd in a few years with their brand new fantastic engine, made $8 billion. You'd share that with us, wouldn't you? Like you'd donate back to the course, right? Okay, just wanted to make sure, okay? I got lots of plans. Like if you got some extra cash from your game engine IPO, I want to take the students on field trips to Stardock, and I want to make sure everyone who wants to go to GDC can go to GDC. Okay, so if you got the money, let me know, because I know how we can spend it, all right? Okay, anyway, just saying. So, particle systems, right? They can really provide this fantastic sense of place and presence and time, right? A snowy, dark night is way cooler than just a black screen, okay? But you can have fireworks, you can control the timing, you can control how things explode, their emission patterns, their emission timing, how many come out. You can change how they shrink over time. Notice, these particles are not only snowflakes, right? But they start off as white, and then as they lose energy, they become green, and they start to fall to the side, right? They have this gravity. You can really do a lot of things. There's a lot of things going on right here. Here, we've changed our snowflake image to be more of a smoky image, and we are sending out so many of them. They are coming out and forming this cone shape. They have a slight gravity that accelerates them north, like air, right? So fire, very hot. Hot air tends to rise, and it rises quickly, and it carries that smoke up. And so we get this convincing effect. But the smoke dissipates and becomes less dense as it spreads out in the air, and so it becomes more translucent. Cool, looks good. And that's a lot of particles right there without any sort of slowdown. This is one of our latter test cases, and if you want to keep up with the instructor solution, you're going to want to have a decent data-oriented implementation. Now, I say that, but you should know I'm not that good at performance myself. It feels like there's always some weird thing I accidentally left in that making everything slow. So, don't judge me if you wallop the instructor's solution in homework 9, okay? Well, you can judge me if you want to. It doesn't really matter much, does it? Okay, so you can also, and this is my favorite effect, right? You've got this cool character. It reminds me of a fairy flying in to say hi to you. It's just more charismatic. People get interested to see things like this. It catches your attention. And you can see that down here, there's just a lack of that spice, that visual flair that we've been looking at. It's just not here in any of these GIFs. So this is what I showed you earlier, the progression of our engine, but actually, we have one more, okay? The data-oriented 2D engine. And in reality, our entire engine isn't data-oriented, or everything would be running a lot faster, but it would probably be harder to script logic. In reality, certain parts of our engine will become data-oriented, and eventually maybe you could flip the entire engine, including the scripting layer, over to a data-oriented approach as well. I think Max, our IA for the course, said he was working on his engine to make it more data-oriented. That's something you could do if you want to, after the course ends or during your final 2 weeks. So, let's talk about particle systems. Particle systems, they are a fantastic opportunity for us to add some data-oriented sauce to our engine without having to worry about converting the entire engine to a data-oriented approach. All right? Particle systems, they are, well, if you've taken 494, you can never, ever have too many particles, okay? And particles are often the key to creating gorgeous effects. This is a 3D particle system. In Unreal, we have this beautiful particle system. I think it's called Niagara. And it is capable of getting you collisions with particles. In fact, we have this beautiful particle flow going through this little valley right here. Smaller game engines have particle systems as well. This is actually Adobe Flash. And particles have been implemented. Oh, yes, here we go.
Never have too many particles in your game. Again, that makes sweeping statements, but it's 1% true. Let's add some particles. We're going to start with the plastic smoke ball and something. We put a little puff of smoke in there. You can use whatever particle engine you can find. It's kind of trash for programmers. These are particle engines because you can make anyone and you're making it the very best one, and then you use it. But it's fun. So don't do that. Just find something that's already made to use it. You can do the plastic thing from programs. Someone's one. Don't listen to him. So we got smoke in the game, like smoke coming up. We can do better. We want to make something with blocks. So we want to make it disappear. Because this is taking a pretty part of this between. But if you can understand the ball, you can see it slowly going away. We can do better. We can do better, way better. So let's make them fall away. Look at that. It's just falling off. We can do even better. Let's add some more stuff. Let's make the balls push the ball. Look at that. And why can spin when we're at it. And now you can tell, like, it's hard to see which, like, the ball fall sort of blending with the other one. So let's
Okay, anyway. So if you recall from EECS 494, for those of you who have taken it, this is a part of the juiciness lecture. Juice is about providing maximal game state feedback for minimal input. So particles in this case are being used to notify the player and help them notice that they have hit a block, okay? Which is what you want to do. When a character takes damage, right? Often you'll have a sound effect, a sprite, you'll have flashing tint on the sprite render, and you often have a particle effect flying out, whether it is blood or the more PG sweat that goes flying. All of these things, all of these effects, some of them particles, are meant to help the player understand what is going on. Particles and particle systems are a core tool that your game designers need to make games that will be successful. So let's see some more particles, okay? Sucker Punch is one of those companies, first-party Sony team, that is famous for their incredible particle system, okay? They've always been extremely good at this, well, as long as I can remember. And this is gorgeous, yeah? You've got this rolling fog that's a bit thicker in the background, okay? Some maybe advection fog or something like that. You've got these nearby particles that seem to have fallen off some trees or maybe from this vegetation down here. It just looks gorgeous. And something to remember is that these incredible particles are running on garbage hardware, console hardware. This is not PC footage, at least I don't think it's PC. They did eventually release Ghost of Tsushima on PC. I think this is probably like PlayStation Pro or something, PlayStation 4 Pro, I don't know. But anyway, Sucker Punch, one of the reasons, if you recall, one of the reasons they have their own internal, proprietary, expensive as heck game engine, and they don't just grab Unreal, they don't just grab Unity, is because their identity is having the best particle systems on the planet on PlayStation, on console. Okay, their engine is optimized and geared for having particle systems that are gorgeous, but on very cheap, crappy, slow hardware. How do they do it? I have no idea. I don't work at Sucker Punch, and I'm not that great at optimizing stuff anyway. But particles are a very, very big deal. So particles, as you've already seen, you can do a lot of things with particles, and we want to give as much expressiveness to our game designers as possible, because particles might be used to represent some dust when someone walks, or it might be used to represent some fog rolling through the hills, or some hail coming down quickly, or some smoke that is arcing upward with a sense of inverse gravity. They need to be a lot of different things, all right? And so we need to give our game designers as much configuration as we possibly can. Things like position, where are the particles going to spawn from, but also things like color. You can see here in Unity, we have the ability to just very easily move our particle system around as a game object, a component on a game object, a component on an actor, in our terminology. And we can also go in and adjust some of that components, the particle system components, tint, okay, its starting color. We can also adjust its speed and also its size. So we can have this laser beam of particles going out super fast. We can also make them big. So if you make the particles big, it looks a lot more convincing as like a smoke effect. Make them small and it looks more like a bunch of bullets are coming in or some hail, right? Small kind of discrete objects are flying. We can also say, you know what? I don't want this cone. I also want a spherical emission. I want to change my emission shape. And I don't want them to continuously come out. I want them to come out in a burst, okay, when I demand. This is the kind of thing you might use if you are grabbing a collectible, and when you grab the collectible, a bunch of confetti bursts out in all directions. It's not a continuous stream. It's just a one-time burst of particles. This is the kind of thing that might happen if Mario lands on the ground after a big jump and you want the dust to fly up, but only once, okay? So you can also choose how many particles you want. You can also say, I want the shape and color and tint to change over time. So a starting color and an ending color. And you have to linearly interpolate between them. All of this is powered by a big particle system component. My goodness, this is an epic component, one of the biggest in all of Unity. You probably won't find a bigger one. And each one of these little boxes, do you see each of these boxes with a checkbox? When you click on it, it opens up into its own section with a bunch of configuration for that particular category. And up there, of course, we have a ton of it already. You are not going to implement all of this, but you're going to implement an important subset of these properties. In many ways, your particle system is going to feel like it was ripped right out of Unity when you're finished with homework 9. And you'll be capable of doing a lot of very, very cool stuff, okay? Particle system components are very common in game engines. Typically, they are exposed to the scripting language, but they are actually, under the hood, implemented in C++. So they are built in, just like your rigid body component, which was implemented in Box2D C++. You are going to implement this component and how it works in C++, and then you will expose it to Lua so that your game designers can configure this particle system and control it. Tell it to stop playing, tell it to start playing, tell it how fast to play. I think that's one of the things you do. I can't remember exactly. But you can see here, right? This is built in. We can define it in JSON, or you can add it at runtime, or destroy it and remove it at runtime in the Lua code if you want to. This is basically the exact same process as what you did in your homework 8 with the rigid body component. Isn't it cool to be like, yeah, you kind of understand how Unity did it, right? Like, you know, years ago, I would use the rigid body or particle system component in Unity and be like, wow, this is magic. I have no idea. They must be crazy smart to implement this. And they are crazy smart, but what you don't realize is that you are as well. And so you can now do that, and it's just like, it's not that big a deal. Just not, right? You are going to implement quite a few of these properties. These aren't all the properties, but these are almost all of them. You can see, you can change the emission angle. You can change the X and Y position of particle emission. You can change the ending color, the starting color. For different channels, you can choose the rotation you're going to start the particle spawn in at. You can choose a range that you're going to randomly spawn them in at. You can change the image the particles are going to use. It would have been cool if we could like specify a list or a table of different images and then randomly pick one of the images, but actually I want to make this assignment not that hard, okay? So only one image is allowed. You can upgrade it later if you want to. Gravity scale, right? Different starting scales, frames between bursts, okay? Yeah, you can just do a lot of cool stuff. One really intimidating thing is that there are a lot of properties you have to make work here. The really cool thing is that most of the properties they're like the same. They're only a little bit different. And once you've made a few of them, you're going to start to cruise and you're going to just roll through the rest of them. And that's part of what makes the assignment actually not too bad. Okay, so some tips for you. You are nearly finished. The finish line is not far away, okay? And even if you're a bit behind, even if you're still on homework 7 or homework 8, you just got to pass that finish line, okay? Who cares if you're in first place? Past that finish line, it's like finishing the marathon. The fun part, the cool part is that you finished a marathon. You don't really worry so much about the time too much. Start early if possible, no surprise. You're going to start to feel your code base's quality as you add more and more stuff onto it. Is it hard to add stuff? That means your code base is a bit sus. If it's relatively straightforward to add new things, that's a very good sign. Your code base is in better shape than you might realize. The autograder off date is in 2 weeks from now, so if you are a bit behind, you can still make this happen. You can still burst through that finish line, but you have to be very smart, and it is crunch time. Okay, that means use all your office hours that's available to you, and don't get too distracted. Okay. The exam is in 2 weeks. You're going to want to use next week to study if you can, and make your own game if you can, and all that. You're going to reuse what you did in homework 8. So hopefully it's relatively fresh. And if you are not finished with homework 8, the good news is that you'll finish homework 8, and then it's going to be pretty easy to quickly finish homework 9 as well. You might want to, I don't think you should sweat performance too much until the end, okay? Focus on correctness. It's okay if you start with an object-oriented approach. I recommend you try and do a data-oriented approach just from scratch because, converting isn't all that fun. But I wouldn't worry about it too much, okay? So you might need to experiment a bit to get the performance that you're after. Or maybe you get lucky and things are faster for you, from the get-go. There are only 5 test suites, and many of the test cases are very similar to each other, so you won't have to worry too much. You're going to implement new features, but the way you're going to implement them are very similar to the previous few test cases you've done, and so things are going to really just go crazy fast, all right? Just not too bad at all. Okay, any questions or comments? All right. The last few test cases are kind of long because they generate a ton of particles. And so, auto grading might be a little bit slow toward the end, but I don't think it's going to be too bad. And a lot of you are very spread out by now, so I'm not super worried about that. The auto grader seems to have done fine for homework 8. All right. So what I want to do is we've talked a little bit about data-oriented design, and the idea that you'll need to use it. And it has something to do with memory. Memory is one of those things, performance in general is one of those things that is so fun to experiment with. And it is such a tease. Oh, it's such a tease. Because I've said it a few times, and I think I've talked to you about why. You will have a tremendous idea for, I can improve my performance by doing X. And you'll implement X to test it. Hopefully you'll do that. And you'll test it. And you'll discover that, wait a second, my performance just lost 20%. And you'll be shaking your head, okay? And this happens quite often. Computer science is becoming more of a science because you need to experiment a lot to figure out what the compiler is going to do and what it might not do, and whether your theory on what will be faster is actually going to prove true in reality or not. But in general, right, performance, you can do testing and you can kind of develop some heuristics. And today I'm going to show you some pretty powerful heuristics that will very often help you. Not all the time, but generally, okay? And so I want to show you some code, all right? I want to show you some code. And this is not very complicated code. Here is a main function. And we have a bunch of experiments here. You can clone all of this if you want to play around with it and experiment yourself. You can find this code later. It's right here on the agenda, right here, workshop. That should be public. And if you look in here, we have experiment 0. Well, what is it doing? It's going to print some information, but we don't really care about that too much. We have a certain number of actors, and we're going to have this vector here. The vector is going to store a bunch of actor pointers for us. So this alone does not tell us a whole lot about where our objects are going to be relative to each other. What we do is we reserve enough space for this actor, these number of actors, and we're going to create our actors in a very simple way. We're just throwing them on the heap. We are asking the operating system to go find some free memory on the heap, which is a slower place to put stuff, but it's a much bigger supply of memory. We probably don't have to worry about running out of room on the heap. If we put it on the stack, we might be in some trouble. So actors are going to be allocated at a random location on the heap. Maybe we'll get lucky and they're pretty close together, or maybe they won't be so close together. Who knows? We are going to give these actors a position, X and Y, and then we're going to push those actor pointers onto our vector. So how big is an actor, by the way? This actor has an integer ID, a string name, a bunch of floats, another integer, except this is an integer array, so collision layers on here. Oh boy, that's going to be kind of big, okay? We have some booleans and then a final integer array to store some associated component IDs. Okay, this is a big actor, right? We're going to see that this is around 600 bytes, I think. That's, that's big compared to what it could be. But actually, in an even bigger game, the actor struct might get even bigger, okay? Who knows? And so that's it. We are going to establish all these objects on the heap. They're big objects. They're randomly placed on the heap. They're not contiguous. And we are going to then start timing, and we're going to iterate through these actors in a naive, n squared for loop. And then we're going to just check. If they're at the same X and Y position, we consider the number of collisions to have gone up. And then once we're done checking them all, we end our timing, and that's it, okay? We report the number of collisions, and then we report how long it took. That's it. That's our test, all right? So, how fast is it going to be? Well, here's something you need to note, because you can get blown up by this. Make sure you're running in release configuration and not debug. Debug kind of makes everything super slow, and it was also messing with my tests and giving some really weird performance data that didn't make a lot of sense. Also, release mode is kind of the closest to the actual end user experience that you're going to get. So you want to test in release mode probably. Okay, so do you want to run this? You want to find out how fast this is? Okay, I'm going to run it. We got two big things, okay? We have 100,000 actors. Those actors are 592 bytes each, and they are at a random location in memory. All right? So I'm going to enter OK, and now it's going. It's going, it's rocking, it's rolling. We can see it's building up memory usage over here. And, oh, it's done. It took 8,000 milliseconds, so 8 seconds, okay? Well, we have a second experiment in here. Experiment 1. Well, what's that going to do? Well, experiment 1 changes something. What it does is it keeps the big chunky actors, those big data structures. They're still going to be about 592 bytes. But if you see here, we are still putting it on the heap, but we're being very particular about where we put these actors on the heap. This code is using a technique that's a little bit rare in student code. It's called placement new, i.e., we are using the new keyword to allocate memory, but we're actually telling it where we want to allocate that memory. So here's how to read this. Right here, we are creating a empty buffer of bytes. Now, we use char right here, but char is just kind of shorthand for 1 byte, okay? So we're creating a byte array on the heap. That's what new is right there. We are making it the size of our actor, so it can fit at least 1 actor, times the number of actors we have, so it can fit all of our actors. It's enough space on the heap to fit all of our actors, and it is a contiguous block of memory. So this placement new right here is saying new, so I want to place things on the heap. And then it is going to be at the location of the actor buffer plus whatever actor number we're at, okay? Adjusted by the size of the actor. In other words, right here we're going through a for loop and we're saying I want to allocate a new actor on the heap, but I want it to be in this actor buffer and I want it to be at this location in the actor buffer. That's where I want you to initialize our new actor, okay? So actors are allocated at a contiguous location on the heap, okay? The only thing that's changing is where are these things relative to each other? Is it at a random place? That was the previous test. Now it's going to be at a continuous location. Contiguous, next to each other. Okay, so I'm going to type OK and let's see what happens. Okay, experiment 1 is off to the races. There we go. With my luck, it'll be like slower. We'll see. Oh, I need to press enter to begin. Sorry. Okay, there we go. Now it's off to the races. We'll see what happens. Gonna drink some of my energy drink. Stay awake. Stay awake. Ooh. Okay. So what has changed? Can you squint and see the change here? What has changed?
Slight performance increase.
I wouldn't call it slight. What percentage is that, roughly?
Well, it's like quarter, 40, 30%.
It looks to me like 25%. Is that right? Around 25% performance bump. Ooh. Not too bad, right? You know, we always want like the 10x performance improvement, but 25% isn't something to sniff at. Okay? And you could test this, but as we have more and more and more actors, maybe that performance improvement actually gets even nicer for us. I'm not sure. We'd have to experiment. So that's really good, but can we do other things to improve the performance of our code? Because you know what's actually happening here? We have this contiguous situation where all of our objects are very close together in memory, so we can just grab them all at the same time. But they're very big. In fact, these actors are way too big. Look at this code right here. We're moving to experiment 2, our third experiment. Look at this. We are going to place things at a random location in memory. So we're going back to the slow ways, right? But actually, we're no longer using an actor because the actor is so chunky, okay? The actor is so chunky. Let's look at this, right? Here it is. The actor has all of this data, but I want you to look at this logic. Our code only cares about what? Our code is iterating through all these actors, but what data are we using within the actors? What do we care about, actually?
Position.
Exactly. We only care about the position X and the position Y pieces of data. 2 floats. That is it. Why are we loading in these big chunky actors just to get 2 floats within them? That's a lot of wasted space, isn't it? In our cache, all of our little bits of hardware that is meant to load this data into memory for us, they're not infinitely big, okay? Like often they're actually very small. So let's look at experiment 2 again. You'll see that actually we're not using the full actor struct this time. We're using something called position component, and the position component has an integer for the ID, and then it has just the floats we care about. That's it. That's it. So how big is this position component going to be as a structure compared to the size of the actor structure? The actor was about 592. Well, let's take a look at the next experiment and run it, and it's going to tell us how big that position component is. So I'm going to type OK. Now look at this. Experiment 2 is going to be the same 100,000 actors, but instead of using the full actor for our calculation, we're only using the component that stores the actor's position data. And that's 12 bytes instead of 592 bytes. Okay? Now, note, we're still putting them on random location in memory. So we're kind of going backward a bit. But we're comparing experiment 2 to experiment 0, that 8,000 milliseconds. Let's find out what happens. I'll press OK, hit enter. Oh, and look at that. Ooh, my goodness. We're already finished. Do you see it? Same location in memory as experiment 0. The only thing we've changed is we've made our data structures smaller. Smaller, as in we've gone from 592 bytes to 12. And thus, as a result, we've gone from 8,000 milliseconds for this experiment to less than half that. Ooh, all right. Feeling pretty good. Okay, better than 50% performance improvement. Not too bad, all right? If you're at a big company, that could save you a lot of money. If you're at a game studio, that could free up a lot of time to make your particle effects even more beautiful. Because now your system, one of your systems, whatever the system this is running twice as fast. You have a lot of time back. You only have 16 milliseconds per frame. That's all you've got in a game scenario. You only have 16 milliseconds. So getting 3 of them, 4 of them back is game-changing for you, okay? Your game's going to look way better now. Okay, so, well, you might say, well, you know, we introduced a contiguous memory optimization and we introduced a size of structure optimization. So what if we do both? In this test, we have contiguous component placement in memory via placement new, and we're using the component, all right? We're not using the full chunky actor, we're only using its component with position data. And so it's down to 12 bytes. We've got both of the optimizations going. Let's see what happens. I press OK. And now, another improvement. Okay, from the size optimization, which was our best yet, we had 3,600. We've now lost, what is that, about like a 33, maybe a 30% optimization on top of our previous one. Crazy. Killer. Okay, with both of these optimizations, we went from 8,000 to about 3,000. Okay? Not too bad at all. 60-70% performance improvement. Super, super nice. And the only things we really did was we shrunk the size of our structures pretty significantly, and we made sure that we're putting them next to each other in memory. Now, there's one more optimization that we can, well, it's not really an optimization. What it's going to do is it's going to do the same 2 optimizations, but instead of placement new, it's using STD vector, okay? STD vector and a lot of the standard data structures will give you that contiguous placement in memory automatically, okay? It's going to do that for you. Will the linked list do that for you? No, I'm pretty sure it doesn't do that. I always forget, why does anyone even use linked list? Like, it's kind of a cool data structure to implement, but I never find myself wanting it. I almost always use something like the just vanilla vector. I don't know. Maybe we should put that in here and just see what the performance is like. That'd be kind of interesting, isn't it? Anyway, I'm going to hit enter and see how their implementation does compared to my, and it's slightly worse. I'm using placement new. The vector is, slightly worse. I don't know if that's just it got unlucky or something, but there you go. It's still way better than everything else. All right, and you'll notice the number of collisions here is the same. So the correctness of these optimizations is perfect. Things have simply gotten faster, okay? And I think what you'll find is that if you really get into a situation where performance is everything, like in a game engine that is correct, but now you're trying to make it the fastest engine because you're up against Unity, you have to beat them. Or maybe you're a high-speed, high-performance trading employee. So you are programming the software that's going to let your traders on the NASDAQ or something get their order requests in faster, or maybe process data faster so that you can notice that the market is turning before your opponents do. You get in, you make the sale, you make money, and you leave everyone else in the dust, right? Then this is extraordinarily important. So you're going to be thinking a lot about where your data is and how to make your data smaller and faster. Okay, so if you're really interested in this and interested in playing around and doing your own experiments, yeah, clone this, all right? Do it. It's awesome. It's super fun. It was fun making this experiment, fun talking about it. And it's very frustrating when I think I have an optimization because I made my structure a bit smaller and then everything is much slower. And it just drives me crazy, okay? So be ready for that as well. Do you know what this is? It's kind of weird. Like, what am I looking at here? What on earth am I looking at? Yes? Keith?
Cache lines?
Yes. This is a cache. This is a cache that is trying to load in the position data of a bunch of birds so it can do some collision detection. Or actually, I think it's actually related to velocity and motion, updating positions based on velocity. Okay? And one of these is a data-oriented design, and one of these is the classic, you know it, you love it, object-oriented programming approach. Slow. Big chunky objects where you've put all the data for the object together so it makes sense in your head, but unfortunately, it's really hard for your cache to deal with, okay? That is what this is, okay? We're seeing a really fantastic visualization of cache utilization in a data-oriented approach versus an object-oriented approach. And this is the difference between a game that can support, a few thousand characters on screen, right? Processing, simulating, updating all at once, a big real-time battle, versus tens of thousands or hundreds of thousands of actors doing their computation all at once, sometimes in parallel, okay? So this is a position-related calculation. What's happening here is that the cache is loading the position data for all the actors that it wants to move, okay? The problem, though, what are these big white gaps in here? We see the position data, the vector 3 is in here. That's great. That's what we need. But we got these big white gaps in here for some reason. And what that actually is, it's all the data that the cache has to load in, but we don't care about it. We just don't care, all right? So the HP of the bird is in here. The speed of the bird is in here. That actually sounds like it might be relevant, so maybe we actually do want to load that. The defense, the attack, the stamina of the bird, we don't care about those things. Why are we loading them? Well, which one of these do you think is going to be faster? And you've seen proof that one of these is way faster, okay?
The data-oriented one.
Exactly. I don't think I've actually said which one of these is the data-oriented one yet, have I? Over here on the left, we have a very dense cache that has a lot of stuff in it that we want to use, okay? The other side is quite slow because our cache just can't fit as many of those good pieces of data that we want access to right now, all right? Over on the left here, I think I counted them up, and I saw that we were holding 75 different positions for 75 different actors into this cache before we have what's called a cache miss. we have to unload everything, and we have to go to a place in memory and load a bunch of data into the cache again in order to get the stuff we want, okay? We have to go do this because we actually just ran out of space in our cache. We just flat out ran out, okay? So every 75 position datums we load in, we have a cache miss here. And our cache has to go back to disk and it has to load some more data. Now, over here, we only get 16 positions loaded in before we get blown up and our cache is full of garbage. And we have a cache miss, all right? And that's bad news. One of these is way better than the other, okay? So when I say cache miss, you might say, well, you know, what is that actually? You heard it's bad. You might have heard it's quite bad. I want to show you one of the coolest websites I've ever seen. This is a website by Colin Scott. And here, you know, it looks kind of weird, you know, when you just look at it. But it's actually a timeline. So I can grab this little scrubber here, and you can see this number. This is like UI made by a programmer, you know. I wish this number was way bigger. So you can kind of see how latencies, the time penalty for accessing different bits of hardware in your computer, you can see how it changed over time. So if you recall back from like your EECS 370, there's this big hierarchy of little bits of hardware relating to memory, you know, where you store pieces of data. And the lowest, closest pieces of memory, the closest bits of hardware to the processor, right? Very fast. The L1 cache is very fast, very expensive to produce. You usually don't have very much of it. And so it's only going to hold your most valuable, most commonly used data. But then you have an L2 cache, which is a bit bigger. It's a bit cheaper. That's why you can have more of it, but it's a bit slower, right? You then have, for instance, you keep going up here, main memory. I think this is what people are usually referring to when they say RAM. Okay, it's like those sticks that you buy that used to be cheap, but now they're like $1,000 for like 64 gigabytes. Crazy. You know, I can't wait. The market waited to collapse and become a disaster until I needed to upgrade my computer. It's like the universe knew, okay, 2026, Austin really needs to upgrade his computer. His old one is dying. This is the moment we're going to spike everything with the data centers. Isn't that just my luck? Well, that's how it goes. Anyway, you can see that the time cost for all this hardware used to be outrageously expensive. And as time went on, we get into the 2000s, the L1 cache is getting quite fast. In fact, all the caching is getting quite fast. The cost of a branch misprediction used to be quite high. It's getting less expensive all the time. By the way, a branch misprediction, what is that exactly? Because this is actually important to data-oriented design.
Basically, when you're just looking at like a branching statement,
yeah,
it uses the previous branches to like
yep.
determine which way to go.
Yeah, I think we talked about this a bit earlier, but a branch is basically whenever you have an if statement. And the branch predictor is going to try and guess which route you're going to go down that conditional statement. And if it gets it right, it's very fast. If it gets it wrong, it's slow. And a misprediction is very expensive. But your takeaway here is that the more conditionals, the more if statements you have in your program, you know, the slower your program might run. So if you can find a way to get rid of some of those, you might get a performance boost. Anyway, you can see that performance improvements have just improved everywhere. But it still stinks, okay? It still stinks. If you have an L1 cache reference, if it's in cache, you pay a penalty of 1 nanosecond. If it's not in your first cache, you pay a penalty of 4 nanoseconds. So a 4x slowdown for a failure in the first level of cache. If you fail and get a cache miss in both of your caches, you then get what kind of penalty? What is this? 100 times penalty. 100x speed penalty. If you if you get a cache miss. You went to look for something because you're doing a calculation. Oops, it's not there. I have to go to RAM. Oh my goodness. Okay, and RAM is usually thought of as being fast, right? Well, what happens if you don't find it in RAM and you have to load it from your solid state drive? A 16, right here, it's a 16x performance penalty on top of a 100x performance penalty. Oh my goodness, that stinks, okay? In other words, oh, and by the way, heaven help you if you have to go to the network for something, okay? You're actually just doomed, okay? You're totally toast. Now, the network can kind of be thought of as an ultra slow hard disk. So that's kind of interesting. This is all to say that you really do want to avoid these cache misses if you can. You really don't want to go to that expensive stick of RAM memory that you purchased off Amazon for $1,000, okay? Cache misses are going to give you a 100x performance penalty, and that's if it's in RAM, because if you have to go to storage, you're just totally in trouble, okay? Like, that's bad news. Heaven help you if you have to go to the hard disk or you have to use a network to get whatever you need. This is kind of an interesting topic for like the MMO architecture course, isn't it? Right? So how do we pack as much information into each packet that we send to our clients and from clients to the server? And how do we make that as small as possible to give us the best chance that it's going to get through unscathed without having to be retransmitted or getting lost or getting congested on the networks, right? So those are really interesting questions. So anyway, this kind of thing, this question is something you have to solve for absolutely critical high-performance code. And I think it can be really awesome. Like, dang, I kind of wish I had joined Sucker Punch, or I've got some students at Bungie who are famous for their excellent game engine and their networking. And I really want to kind of call them and hit them up and ask, how they're doing this and how they optimize, right? This graphic right here is from a really great talk by Elizabeth Baumel, who works for Unity, at least she did at the time, and she gave this talk at GDC a few years ago, talking about why game developers and designers should be thinking about data-oriented programming and not just about object-oriented programming, which most people are used to, all right? Because data-oriented programming is a little bit more awkward to think about, but it's much more efficient in many cases than object-oriented programming. So, a question then, how many of you have done object-oriented programming? Any of you? How many of you definitely did it, because EECS 280 and 281 teach you object-oriented programming. I know you did that. How many of you would say that your engine is object-oriented? Because I would probably say mine isn't very object-oriented. I don't really use many of the benefits of object-oriented programming, like polymorphism. Mine is more of like just a kind of, I don't know, just kind of a C-style engine, if you think about it. Yeah? Yeah, you use it? Okay. So, if you use object-oriented programming often, you're more used to something like this, okay? You will create a class or a struct. You will design your struct and class to bring together related data for some sort of, entity in a real-world sense. A dog has a hunger value. It has a height. It has a weight. It has a social value. You're bringing all these pieces of data together, not because the pieces of data are used in similar calculations, but because these are things that a dog has. It's an easy way for human beings to think about code and data. You might even put functions into that dog, though I don't think functions actually bloat the object due to how functions are stored by the compiler. It's the data that is the problem, not the functions. Okay, you will then typically store an array of that type of object. So here are all of your dogs. If each dog has an HP, an attack value, and a defense value, you would just kind of store those objects in an array. In other words, arrays of objects. It feels very natural to us. When you want to deal with those dogs, those objects, those actors, you will iterate through those actors, that array. You will load the entirety of the actor into your cache, and that's the main problem here. And then you'll have access to everything, even if you don't need everything. That's the main problem. You end up with this situation right here. What happens if you have some logic, and that logic only cares about the attack value? Well, you still have to load HP and defense, okay? And I'm really surprised that compilers don't optimize this. It feels like you would be able to do it, but I'm not sure why they tend not to. I really wish I had a compiler friend. Maybe I can talk with the compiler faculty and get their thoughts on why they're not able to do this very effectively. But shouldn't you be able to basically break down your logic that follows and go, this array is only, this for loop is only using these particular members. Let's automatically create some sort of sub-data structure. Well, but then you get into a ton of questions about how you're going to update that sub-data structure and what if they desynchronize. And maybe that's why, it's just too complicated. The compiler programmers, the compiler researchers, they can't make assumptions often about what you want and what you might do. Okay? If they can lock down what you can do and make assumptions about that, then they can optimize stuff, but I think that's probably the problem. They think they know what you're going to do, but they can't guarantee it. And if they can't guarantee it, they might accidentally have the compiler break your code by trying to optimize it. That's what I would suspect, okay? That's also why languages that are new, like Rust, can add some new features that allow you to specify things to help the compiler do a better job compiling and optimizing your code, okay? Have any of you done data-oriented programming before? And I almost guarantee it that you have. And here's why, okay? I think I might have misspelled accidentally there. Does it have two C's? Did I get that right?
What's that? A-L-L-Y.
What? A-L-L-Y?
Accidentally.
Oh, yeah, okay. Yeah, I think I messed that up. That just looks weird to me. So maybe I'll fix it, maybe I won't. Okay, so a quick story. I was in EECS 183, and they had an assignment where logically we were dealing with objects, okay? Like students. And we had a bunch of students in an array, and they had grades, and they had like a stamina value, I don't know. But the course didn't introduce structs yet. So structs were not allowed, as far as I understood it, structs were not allowed by the assignment spec. So I'm thinking, oh man, like what? Structs would be perfect for this particular program, for this project. But I can't use them. So what do I do? Well, I was thinking about it, and wait a second, I can emulate structs. Okay, I can emulate structs by doing this. And this is exactly what I did. I didn't know anything about data-oriented design. I didn't know that I was giving my program a notable performance boost by doing this. We have here a bunch of arrays, and each array is focused on one property, okay? We have an array of HP values. We have an array of attack values, an array of defense values. And we know that the number of actors we actually have is 5. This is going to look really strange, but we've gone from an array that holds objects to a bunch of different arrays, that hold different properties. This is sometimes said to be objects of arrays, but I really don't like this phrase. Really, you've taken each property of your struct and you've broken it out into its own array. A question then, where did our actors go? We have a bunch of HP values, a bunch of attack values, defense values. Our actors have to be here somewhere. Where did they go?
Our actors are the indices.
Bingo. Our actors have disappeared. They have become implicit, ephemeral. They have dissolved. They're still there. They're just hard to see. Now, our actors are not identified by a struct, but by a number, by an index. Okay? And if you want to iterate through those actors, you simply use the same index to access all of the different property arrays. If you want all the information for the 0th actor, then you just put a 0 in here. And boom, you've got the HP value for the 0th actor, the attack value for that 0th actor, and the defense value for that 0th actor. Okay? So now it is with a simple ID, an index, that we're able to look up the data for our actors. And when we do this, we only grab the data we want. We're not grabbing the whole darn thing. Okay? This starts to feel kind of similar to a database, where you might want to look up a person with ID, 494440. And then you can use that ID number to grab whatever column you want in that relational database. Well, if you think about performance, this is surprisingly much better with this tiny little change. Our code has maybe gotten a bit uglier, maybe, but the performance is weirdly better. We are no longer required to load the entire object, only the things relevant to our calculation. So, for instance, this is a big improvement. Right here, we are iterating through all of our actors just like we were previously. But now you can see that there is no reference in this logic whatsoever to the HP values or the defense values. The only data we have to load in is a bunch of attack values, which means we're not loading in the whole beefy struct in order to do our calculation. We're only grabbing the values that we actually care about, which is pretty sick, okay? We only care about attack, and so we get this really nice dense utilization of our cache. Fewer cache misses means better performance. So when you say we're becoming data-oriented, I want you to know that just by thinking about your data layout, where is my data? How am I accessing my data? Which pieces of data do we actually care about for which actors? You are becoming more data-oriented just by thinking about that stuff. I have a question for you, and this is actually a problem I first saw in 370. It's that important. You'll see this problem on exams, and you'll probably see this on interviews as well. It's a classic, and it's really cool. I also thought it was super confusing until I learned more about data-oriented programming and caching. Here it is. Which of the following lines of code will be faster? And I see some smirks. You're like, oh yeah, okay, I knew this was coming. It's an old friend. You know what's hardest about this problem to me now? I'm like, man, my eyes, I got old man eyes. I'm only 33, but those J's look a lot like eyes, and those eyes look a lot like J's. Yeah, one of these is wildly faster than the other. It's crazy. A reminder, if I look at you and don't call your hand, it's because I think I might have called on you recently. I might be wrong. The cache within my brain is a little bit funky sometimes. Sometimes it's a bit buggy. William?
Left, because numbers are right in order if you go through by J instead of I. If you do the right side, it just jumps through the array, goes back, not fast.
Yeah, which one are you saying is faster?
The left side.
Yep, definitely, the left side. Yep. Okay, well, how many of you said the left side is definitely faster? How many of you are like, I don't know. Yeah, you don't have to admit to it. That's how I feel. Whenever I see this problem, I'm like, wait a second, and I have to look at it for a while. And then I remember, okay? The real thing here, the only thing that's really changing is the inner loop versus the outer loop. Which are we running through first? Are we running through the J's first, or are we running through the I's first? And you can see J and I is the inner part of the array, and J is the outer part. And so I and J are used to figure out where we are in memory, but iterating the J is what's going to move us through nearby contiguous memory. And here's basically how you can look at this, okay? In memory, we have a bunch of values. Each of the first index, i.e. the I, is going to be a different chunk of memory, okay? So as we move the I forward from 0 to whatever number it's going to be, we are really hopping to like a pretty distant place in memory. But if you advance J from 0 to 1 to 2 to 3, you are just checking and accessing memory locations that are like sequential. They're right next to each other. They're contiguous. Okay? So with this left approach, what's happening is we say first, oh, our I is 0, which means we grab this particular array. When the cache goes to grab some memory, it doesn't just grab the memory you ask for. It grabs a big chunk, okay? It grabs a huge chunk of memory, load it all in. Even if you need a little piece, it's going to load a ton of memory. And fortunately, it's going to load array 0, 0, which is what we asked for, but it's also going to load in array 0, 1 and array 0, 2. It's all right next to each other. Might as well grab it, right? And so it's going to load all of that, and we can just go and we can process all of these things without going back to cache and loading more stuff. We get through all of this. We do all this processing, and only once in a while, when we're done with the whole chunk, do we go back and load in more stuff into cache, okay? And we load that in. So we've done this, and we basically only had to hit the cache like twice for a bunch of data, okay? Now over here, it's a disaster, a complete disaster. I think this is called thrashing the cache because it's being so violent toward it. It's very mean. What happens is the first thing we ask for is, just like previously, 0, 0. I is 0, J is 0. Here it is. That's the thing we asked for, so it loads this in. Now, the next thing we ask for is not array 0, 1, which is in memory. We already have it. No, the next thing we accidentally ask for is array 1, 0. Why? Because in here, the inner loop, the I, is what's always changing, okay? Changing very often. And so instead of using this data that we had in our cache already, we say, oh, forget that data, and jump over here and immediately trigger another cache miss and load this stuff. Oh, it's awful, okay? It's a disaster. And we're going to keep cache missing all the way down, and then we're going to come back up here to process this column, and it's going to cache miss on all of these too. Okay, it's a disaster. You couldn't design it worse if you tried. Anyway, so, yeah, it's a disaster. Horrible, very slow, sad. Data layout is a very big deal, and the order in which you access things is also a very big deal as well. And I said this before, but this is one of the big reasons people are down with C and C++. These are languages that give you a lot of foot guns, so it's easy to hurt yourself if you're not careful. But if you need all those special tools to manage memory and where things are, then you got them. They exist. In other languages, you're just out of luck. There's really not a whole lot you can do. So, how do we start getting this kind of stuff into our games? That's a very valuable question, okay? A common data-oriented approach is to do things like this. So, in your particle system, you might be very tempted to create a structure called particle, and it has all this data. What color am I? What position am I in? What is my velocity? In one structure, very tempting. But breaking it out into a bunch of arrays or probably more wise, something like a vector that can grow, because you don't know how many particles you're going to have. That is something that you could use. I don't remember if there's a max particle limit that we put in the rendering.config. Gavin, you're already midway through the assignment. Is there like a max particle limit that we enforce on homework 9?
No, I think it explicitly says that there could be like an unlimited amount.
So in Unity, there is a max particle limit. And one of the reasons you might do that is because you then don't have to use a vector. You can use just a raw array, and you can even pre-allocate a lot of space if you want to, which is pretty awesome, okay? You might get a speed up doing that. Okay, so you can think of each row as a property, each array as a different property of your object, and the columns expand as you get more and more objects, more and more particles. Each column is an actor or a particle or whatever you're making a lot of. If this reminds you of anything, it probably reminds you of a relational database. So for instance, if you are using something like SQL and doing queries, you might end up with a table that you're making or querying, and it might look something like this, okay? You might have an actor ID column, 0, 1, 2, 3, 4, 5, right? And you have all of these columns that are properties. Each row, in this case, is a actor, and you can look them up based on different properties, and it's very fast. Databases are very, very fast. Now, this isn't quite the same. You see, it's a transpose. So here, the columns are the actors, and here, the rows are the actors. But it's basically the same thing, okay? So our current object-oriented architecture is kind of hideously not data-oriented at all. We have a lot of actors, and those actors tend to be on the heap, often in random locations. Okay, well, that's not great. In order to access an actor, we have to load in our cache and dump everything else, and then we might not get any other actors or the components that the actor has, because each actor has a bunch of components. These are Lua refs. These are probably on the heap as well, possibly in random locations, and that kind of stinks, I guess. And so every time you load an actor, you are dealing with caching misses, probably. So, not so great. What if we could organize these components and shrink them? What if we could do that? Well, there's a very powerful data-oriented architecture called an ECS. Does anyone know what ECS means? Yes.
I was just going to say that's up there, entity component system.
Brutal. Yeah, I got wrecked on that one. So, sometimes I forget exactly the contents of my slide, and I don't quite notice. So, I think there are two things that make entity component system tough. The first thing you run into is that entity, component, and system are three words that you've seen before, and you already have a notion of what they mean in your head. Unfortunately, in ECS frameworks and architectures, entity, component, and system kind of mean different things than what you're used to. So if you ever heard the phrase entity component system, know that it's not referring to the systems that you're used to. It's not referring to the entities you're used to, and components are kind of a different thing than what you might be used to in Unity or in your own engine. It just means different things. The second thing that makes ECS quite difficult are a few interesting questions I'm going to leave you with, and then we're going to finish on Wednesday. Let me show you something. If you have a bunch of arrays that represent different data for your actors, what happens if an actor is destroyed? What do you have to do?
You have to find a way to nullify all the array values or destroy it.
Yeah, you need to wait a second. We have actor 3 right here, this column right here, and actor 3 was just destroyed. So what do we do exactly? Do we like delete this column? And now all of these arrays now don't have 5, but they have 4 columns. Well, doesn't that mess up the IDs of people here and here, these 2 actors? Because now their ID that they might be storing internally is not their index position in the arrays. Their index position just changed. Well, you could also say, maybe I will zero out the 3rd index. Well, how do you know that that is an invalid actor now? And aren't you wasting space? What if you have a lot of actors that you just destroyed? Are you going to reuse that space? When you create the next actor, are you going to add a new column to your vectors, or are you going to know that actor 3 is available and slot yourself in there? What happens if you have so many arrays? You have an array for position data. You have an array for attacking data for all your actors. But then it hits you. 90% of the actors in my game don't have HP. They're like tiles. They're like platforms. Maybe they're invisible, keeping track of different data for different gameplay systems. Are you telling me that the 957 tile actors that comprise the visuals of my level are all going to have an HP value that we never use or care about? And we're going to have this gigantic set of arrays, and it's just burning space. Suddenly, we don't have any RAM left because we're wasting all of our memory. What do you do if an actor doesn't have some data? You don't want to waste space, but you also probably don't want to be messing with the indices, because if you say, well, my tile actor, which represents a chunk of the background, it has position array, but it doesn't have an HP attack or defense array, well then now our arrays don't have the same length, which means you can't use indexes anymore and IDs to actually index into them. Uh-oh. Okay, this is getting kind of hard, isn't it? This is kind of a spooky problem all of a sudden. It seemed so simple. Well, fortunately, homework 9 doesn't require you to do an ECS. But it's a very interesting problem, isn't it? Maybe I should put like a problem on it on the exam. No, that'd be too mean. Okay, I'm not going to do that. I always loved when I was taking an exam and I got a question on a topic that's like, I've never heard of this topic before in my life. And I watched every lecture and I did every homework and project. Brutal. Like, it took humanity literally like centuries, millennia, to figure out how to solve this problem, and you're asking me to do it from scratch in like the next 20 minutes before we run out of time on my exam? Basically, at that point, you're just filtering for people who looked it up by chance before the class even started because they did some cool hobby project with an ECS or something. That seems very strange to me. Yeah. And not something I'm going to do to you on the exam, okay? Anyone have any questions? We're going to come back and talk about this more on Wednesday, I think. In the meantime, I hope you are starting to have a good time with these assignments. I know they're hard, but I hope that at least they provide you some satisfaction and some interesting stories to tell your friends and future coworkers and stuff. I'm going to be around for the next 2 hours. You can hang with me and get started on homework 9. Sometimes I actually haven't looked at homework 9 staff solution in a year. So sometimes if you're the first person to ask me about the homework, I have to actually look at the solution again to actually remind myself of how we did something. But I hope you'll forgive me for that. It doesn't take too long. Okay, I'll be around for the next 2 hours. Yeah, let me know if you have any questions about the industry or just want to hang or talk about games or game dev, or if you have questions about any of the homeworks or the exam, how to study or make games, or if you want to just play some of my test cases. I made them even harder, okay, just for you. And I'll see you next time, okay? Take care, everyone. Good to see you. Get some sleep. Make sure you're eating all 3 meals, okay? You know, these courses are hard enough if you're not sleeping. You want to make it even harder? Professional difficulty mode challenge run. Have you ever seen those challenge runs on YouTube? Where it's like you beat Resident Evil Requiem on the hardest difficulty. Good job. But actually that's nothing, because now you have to beat it with only using the starter pistol or only using the knife. Or you have to beat it without killing a single zombie. It's crazy. Or you have to beat it while walking through the entire game. So you can't even sprint once. Ooh, it's challenge run time. All right. Okay, anyway, I love watching that stuff because you say to yourself, it's not even possible. This can't be possible. Beat the whole game on the hardest difficulty without even sprinting, and then you have to watch the YouTuber, and they show you the research they've done to discover, like, normally you can't outrun this enemy by just walking, but actually, if you shoot it with the pistol once in this certain location, it will stumble. And then you have to walk at this angle precisely, and you'll escape it by like the hair of your chin. Awesome. Anyway, okay, I'm going to let you go home now, all right? Goodbye, everyone. It was good to see you. All right, everyone online, it was also good to see you. Kind of. I didn't really see you. But we'll see you next time, okay? Bye-bye.